So today we go back to the dark ages of computing. So I'm Vincent Lafage from HPC Lab, and I will start with people here asking for a quick show of hand. Who has some practice or knowledge of Fortran? Ooh, not so many. So I guess that the next question, which would be on who has practiced with modern Fortran, is not necessary. So before entering the slides themselves, for the exercise, you can use the images on Kubernetes on Must. They have been tested. But as many here have not seen the marvels of this venerable language, we'll go into some detail. So I will continue with the initial definition of Fortran. It was an acronym for Formula Translator. So what is obvious for us that any language, and in particular any compiler, will take a human-readable formula and make it some sequence of assembly instruction, was absolutely not obvious 70 years ago. In fact, when you have a mathematical expression, you need to split it as an expression tree. This is quite of classical parsing. And sometimes you may even you can express the same expression with different trees, some of them being more efficient to evaluate. So not only this compiler is among the oldest, it's also the oldest surviving one, the oldest surviving language of this era. And it's the oldest optimizing compiler, because the first programmers would have some contempt for Fortran, as they would believe that assembling by oneself, writing assembly by oneself was the right way to go. Hopefully, we don't have to follow this path. So among the things that did not benefit to Fortran was its fixed format. It was, as we'll see, on punch cards, and this was not encouraging what we would see as the basic of good software engineering, indentation. When you have less than 66 characters for your line, you don't lose many of them in indenting. It was rather computation-oriented rather than system, so it would be a pain to write an operating system in Fortran. And it had really a few types: integer, floating point numbers, and characters, then logicals, I mean Boolean. So the first standardization started in the United States with Fortran 66, that I will dub Paleo Fortran. Already in 68, it was described as old-fashioned, and I was not even born. In 77, the next version came at the international level. Influence of structured programming can be felt to some respect. It's still fixed format. And the procedural paradigm of this high-level language means it is able to handle the second abstraction, the control flow abstraction. So what a lot of Fortran come from these two standards, 66 and 77. But every workstation and every workstation producer would provide you with a Fortran compiler. There were no open source compiler before '89, and it was not even a real compiler. It was a translator from Fortran to C. '88 was, of course, a missed opportunity to make history, and all the following standards of Fortran were similarly delayed. So the standard appeared 3 years later, called as Fortran 90. And this is a totally different beast on the one that we'll use today. Then they introduced free format, among others. Then the first open source compiler appeared for Fortran 77. You got dynamic allocation in 97, and then the first open source compiler in early 2000. So G-Fortran is the follow-up of G95, and this is the one most of us uses. So the question is open since at least 68, as Fortran the future, and you have this paper by Metcalfe, who was very instrumental to try to push it on CERN, but this era was the era of the Great Divide when science was no more in Fortran. C++ started invading. Yet, we have to go back to number and study things from a practical point of view. On this Archer 2 supercomputing center, they took a poll and asked users to describe their usage per language, to declare the language they were using on the supercomputer. Then we had a reply. You can see the line, the URL here for the detail. You had 62% of the project that were in Fortran, plus some undeclared 22%, which means Fortran is anywhere between 62 and 84%. And only less than 2% of Python, 6% of C, 7% of C++. So Fortran has still a huge share of high-performance computing, and I guess for a long time. So if we want to, we will not enter all the details of the syntax. You have pretty obvious things, even if the style is quite verbose. It started with all the aspects of a procedural language, and particularly with the 77 version. It was slightly amended in 90 and 08. From start, you could have some modular practice with the common memory zone, but at this time, it was only seen as a way to save on memory rather than use it for software engineering purposes. It was improved in 77 and got the best in 90 with the notion of module. And it was on this module and type set that object-oriented Fortran appeared in 2003 with extends and inheritance. From Fortran 90, you have allocate and pointers. So don't see this as C-like pointers. These are Fortran pointers are used in the way God intended pointers. It is for referring to something or not to play with memory. Yet, starting with the 03 version, you can interact with C pointers, and you have to deal with the corresponding problems. Fortran is, of course, not what we would call a functional language, but it has some functional paradigm aspect. Starting from the 90s, we have the recursive possibility in Fortran. We have the intent of parameter that led in 95 to the notion of a pure function that we have already seen as a good thing to express concurrency. And elemental function that I encourage everybody to use, which are auto-mapping function. An elemental function is a function that will be pure and also, when given an array instead of a scalar, apply automatically, getting rid of the need of writing a loop and saving on the size of your program. So from Fortran 23, which is not really implemented in any compiler that I know, you have the simple attribute for function, which are purer than pure. It means not only it cannot have side effect, but it is also, it has to depend only on the argument of the function. It will not modify, and it cannot read argument data beyond the arguments of the function, which opens for some simplification from the compiler. Concurrent programming started with Fortran 90. We'll discuss in more detail the array expression and the infamous for all loop, which you should not use anymore as it has been replaced by do concurrent, which is very much what we want to express high-performance expression. Distributed Fortran started in 2008 with co-arrays. Really, there is much to be explored here, but it's still difficult to practice. And it has been yet extended with the notion of team in 23. The really missing paradigm for Fortran is the generic programming. You could, from the start, do some pre-processing, which is not a very nice way to do it, but we can do it. You have had intrinsic generic functions from start, so don't use a separate A-log, D-log for single precision or double precision function. And it really started with interfaces in 90. And starting from 03, you have parametric types, which are a good way in the right direction, but they are not as powerful as the name implies. So much hope is put in the next version, maybe Fortran 2028, that would have templates which are parametric modules. So for more detail, I give you these two pointers. These URLs are linked to the French version, but an English one certainly exists. So the first problem to address when speaking about Fortran is its image. It has a lot of sociolinguistic aspects. It is considered something for dinosaurs in the Jurassic Fortran because it has a supposed style. So in the same way that in the 80s, people would say that basic programming is not, basic programming is not basic programming. Fortran programming, modern Fortran is not all caps, is not Fortran programming as people would imagine. Because of the fixed column format, there is no indentation that were not even a thing before 64. Some people mention the infamous mix of language, something that existed under the name of Comtran and was a mix of COBOL and Fortran, all that you don't want. So people also believe that Fortran is written in all cap. So stop this. The Roman Empire wrote in all caps. They fell. I say this. Make what you want of it. You had two short identifiers, only 6 characters, and the worst of all was implicit typing. All variable before H were real, GH, and starting from I up to n, you add integer variables. So this auto-typing led to a lot of bad practices that we have to correct when pushing this old wisdom to modern environment. And when you were declaring as common variables, common is something in Fortran when you want to have the equivalent of a C struct that will be replicated in your various functions. And so when you declare, you have to redeclare all the variables in the same order with the same type, which can easily lead to problems. Recently, I was presented a main program with almost 10,000 statement line of code. This says the kind of problem you meet when you find legacy code. You cannot put it in your brain in one go. You have to split it in some sense. Okay, so all the go-to laws, its overuse, the infamous arithmetic go-to on the spaghetti code that it deals, that it leads to, are really a problem. But when you look at this scheme for a modern Fortran program, so this is taken from the Idris lecture from Patrick Cord, you will see that you have your main program with internal sub-procedures, subroutines, and using modules shared between a public part and a private part. So we can also adapt to older libraries where subprograms are not related in any kind of controlled sense to the main program. So there is a lot of work to put these external libraries in a modern approach. So when you want to push your legacy code to modern Fortran, it's not simply by changing the format to a free format. You have some tools that allow you to do it. The initial convert tool by Metcalfe, a bit difficult to use, but this is not the only one. And you should really benefit from the next version of the language to express your code. So if ever you have some legacy Fortran to deal with, please use the SPAG program. For the academics, it has a free version that you can get on this link here. And it will take your old, barely readable Fortran to this kind of more modern structure. So it exists, it has been existing for 25 or maybe even 30 years. It is well tested. And nowadays, since about 1 year ago, you can also use it to transfer all your common variables to modules, which are really the way to go. So please use it. This SPAG program has a lot of configuration. You can select some parameter, whether you want to only add implicit known, rewrite all in Fortran 77 style or in Fortran 90 style. You have also item when you want to automatize the translation from common to include, common and include to module. You can also add intents to your function's arguments. And then a recipe has emerged. You want, when you get legacy code, the first move should be to get your code under some version control system, Git or Mercurial, and to add some build capability with at least a makefile, but CMake is Fortran friendly. And nowadays, as all languages have some package manager, you have FPM, the Fortran package manager, which is quite modern. You have a lot of linters. If you want to lint some initial Fortran 77 code, you can use ftn check. You can also activate all the warnings that you can get from your modern compiler. You should declare everything, either by adding implicit known directly in your code and then solving all the complaints of your compiler. You can also double down on it with the f implicit known for the G-Fortran compiler or mdecal check for NV Fortran. And beside the Fortran 77 linter ftn check, you have Fortitude and Camfort for modern Fortran. Camfort is in Haskell and Fortitude should be in Python. They check various aspects of modern Fortran, and they are very painful, but they tell you to comply to the most modern aspect of the norm. You should also proceed with some cyclomatic complexity analysis. Lizard will give you what among your functions are the most complex. So cyclomatic complexity is, roughly speaking, the number of jumps you have, the number of branches you have in your function. Each loop will open a branch, so it will be counted as one. As a rule of thumb, if your function has a cyclomatic complexity of 10, it's okay. 20, it's still okay. I have seen 600, really not good. What happens usually in legacy Fortran is also a lot of code duplication. People didn't wait long for cut and paste. And you have tools such as Simian that will tell you which part of the code are copy of one each other. Once you have done all these steps, a lot of work has been done, but it really starts now with the use of SPAG I have already started to describe. You can start either with the old SPAG and converting each command by hand, or with the help of SPAG and doing it automatically to convert command to include and later include to modules. Of course, this is also the time when you move from the fixed format of Fortran 77 to free format. Sometimes, a common practice of the old time was people would declare values of the variables with the data statement. And it has a side effect which is not well known. It makes your variable static on top of initializing it. So this is not what C user would expect, and it leads to some misunderstanding. And most of the time, all your physical constants will be declared in this way: initial value with the data statement that makes your variable static. So for only the values that are intended as constant, you should turn it to parameters. Parameters is a kind of const or constexpr or static constexpr or consteval plus define. The good point compared to C-define is that it will be replaced directly, except when you have an array of parameters, which are rather recent aspect. So you don't find the object symbol, the symbol in your object file when you use a parameter with the same variable name. It is copied as if it was the preprocessor, but it has a type. The compiler was conscious of this variable, even if it's hard written. So use parameter as much as possible. So for all procedure arguments, you should declare their intent. Are they in variable, out variable, or in out variable? And then you can move as many procedures as possible to pure. And then we should have a small step, small reflection here. Once your variable is pure, you cannot have side effect, so you cannot have input-output. So you cannot debug your pure function in the old way with a print or a write. You have to know about your debugger. And another way is also to have a lot of unit tests to deal with problem of your function. Of course, the next step is to get all possible procedure as elemental. It will save you loops, possibly. And as much as possible to express, as we'll see later, all your floating point variable with a generic kind. So standard Fortran as C and other language have single and double precision as encoded in the IEEE standard. Many Fortran compilers have a quadruple precision, which is not in silicon but emulated with software. And so you take a factor of 10 in your speed, but you have a lot of accuracy. We will see tomorrow that this is not the ultimate solution. Some format that is not well known is the long double of C, which here is supported by Fortran and not even by the Intel compiler, which is intermediate between double precision and quadruple precision, but it's in silicon, so it's fast. It cannot be vectorized, or for the last 35 years, it has not been vectorized. So you will not get the most speed up, but you win 3 more digits, which are a good thing. Yes, and as I mentioned, I am not sure why, but in legacy code, you find a lot of DSQRT, dlogs. When your argument has the right kind, if it's double precision, you don't need to explicitly write that you are using the double precision function. So use the generic form, it will make your code better. Okay, and now for HPC-oriented refactoring, you want to convert all your do and do loops that are not iteration but enuplication, when each step of the loop does not depend on the order it is executed in. You would better have elemental function call. So a for all loop existed, and nowadays it's deprecated in the standard. So as the question happened, for loop were limited to array assignment. We'll see array expression. So what was the benefit? Sometimes in an array assignment, as you have no index, you, in an array expression, if you have no index, you cannot fill your array with index-dependent value. So for all was here to solve this problem, but it was really limited, and it did not allow inside the for all loop elaborate structures. So for all and do concurrent loops, the modern replacement share the same aspect. You can only call pure function inside the do loop, do concurrent loop. But yes, the new solution is do concurrent. Most of the time, I will advise to use more appropriate functions. So nobody here would write a matrix product or a dot product. You have function to do it, and we can hope that the compiler optimized it for us. That the compiler will use the BLAS library to compile it for us, to compute it for us. Okay, so as we have been speaking of unit tests, here is some example of PF unit by the NASA. So you have F like Fortran and P as a parallel Fortran because the NASA wanted to have their test work on multi-thread when possible. So you see that we have Doxygen kind like of commands where we can document in UTF-8 the name of the author, Euclid, and describe the function as a general algorithm for factorizing an integer into its prime factor. You can describe the parameter and the variable in turns, and you can play with a list directly and extend it, even if this is certainly not the most efficient way to do it. It's a dynamical list that you can initialize to an empty vector, but then you have to precise that it is an empty vector of integer. So as you can see, this modern aspect is quite different from the image of standard Fortran. So this is the module with the function, the pure function divisor list that you want to check. And then the test suite is in testdivisor.pf. So it contains a non-Fortran statement that will, for the various asserts that you want to test. This was for the typical kata of Euclid algorithm on divisor lists. So it was developed using test-driven development when the first test should check that when you want the list of divisor of 1, you will get some empty list, empty result. The divisor of 2 will be only 2. The divisor of 3 will be 3. The divisor of 4 will be 2, 2, and so on. So as this PF format is not pure Fortran, you guess that the PF unit framework relies on some parsing program, and it's in Python, but please use it. It helps a lot. So another classical kata is here. Sorry, it's really small. When you want to produce converting an integer to its Roman numeral expression, you will write this small function step by step in TDD with the corresponding test suite, test Roman numeral. Okay, so the practice here was to put every test in one simple test example. This is not the best practice, but it's also good to see that it fits in one page. in order to see some aspect of modules and parameters, so you can document, you can get a list of physical constants that will be useful. And for your documentation, please be expressive with Unicode characters. You can call pi as pi, square root of pi as square root of pi. And it doesn't require that your compiler understands any of UTF-8, as it is only for comments. Okay, so brief pass on the object-oriented aspect of modern Fortran. You can have a public type in your module test, which will have some allocatable component. This type being extensible, it will have a destructor. So we call, this with the final attribute. And we name the function that is defined over here and will deallocate your dynamic component. You can describe all the methods inside the type, which is inside the module. And for the constructor, you can rename it with an interface with the same name as the type itself. And here we will have the constructor, being private. And here we see this, the list of functions and their implementation. And so the constructor is not explicitly called as it is private, but you use the default constructor and you initialize your object. So you see this block and block structure, which is very much more verbose than the curly braces of C and C++, but plays the same role. And it means that you can define some block with declaration inside. So you will limit the scope of your variables. The next aspect of Fortran 03 was the possibility to bind your C libraries, because a lot of useful programs, useful libraries exist in C. And then you provide the name of your C function and you turn it into a Fortran scalable one. And you can declare this as pure. So you do this at your own risk. You tell the Fortran compiler that the C function is in fact pure, but the compiler has no way to test it. So this example was providing some interface to decimal 32 kind of float. So some people want decimal floating point number instead of binary floating point numbers. The rounding are different, a bit less surprising sometimes for us humans accustomed to decimal numbers. And so this useful C library can be translated to a Fortran library if you want to check that your binary floating point number leads to similar uncertainty to your decimal floating point number. The speed will not be the same one, as decimal floating point number are emulated by soft. The next level, when you have simply redefined C function as Fortran function with a SYN binding, is to provide a SIC binding, one that will allow operators to sum or multiply and so on directly decimal numbers, so that you don't need, with the SIG binding, any kind of change of a program that would be expressed in binary. You can use you just have to change the type of your variables, plus the input-output. If you really need assembly in your code, so there is no way to write the assembly directly in Fortran, but you can have some C function in which you can use this syntax to have your function in assembly, and then you will call your C function from Fortran. Okay. Maybe not so useful, but we can do it. Okay, so after all the nice things that we have in Fortran, what do we miss? Okay, so some object-oriented people will tell us that we have no multiple inheritance, even if maybe we can replace it with the facade pattern. There is no first-class function, as we can only pass pointers to function. There is no exception handling beyond the input-output exceptions and the IEEE floating point exceptions. No assert for test, so we have to replace it with PF unit style frameworks. No genericity, so there is a lot of effort from the committee, and you can find what it should look like on the GitHub link that is here. So Fortran 2028 will, in the best case, be accessible in the 2030s. But I would really like to see this. Why is genericity so big of a deal? So for computing, we would like our program to change from kind of float to kind of float without us having to rewrite a lot of things. So we already have some way to do this, but it's a bit tedious. You have to recompile a lot of things. So beyond this computing aspect that are dear to my heart, I would say that what makes Fortran so old-looking language is it missed the standard library that C++ and other languages can boast about. Because no genericity in Fortran means your data structure are array of anything but arrays. No list, you can code it, but you have to recode it for a list of float, a list of double, and so on. No tree, no graph, no elaborate things. It led to a very painful YouTube video where somebody in 2012 boasted at a Python conference, Python is faster than Fortran. Of course, this is fake news. What led to this kind of false statement is, as there is no hash map in Fortran, in the standard, he was comparing some merging of data with hash map in Python. And as it did not exist in Fortran, he took two arrays and had a square of n algorithm instead of a log of n algorithm. So this kind of bad faith was really not a good thing. Okay. Some other part which is missing is the absence of const attribute. So we already have parameter that I spoke of, but we cannot go further on the functional way by having immutable data. behind the parameters that are not dynamically immutable. So we have to play with the intended parameters or the protected attribute in modules to have some equivalent functionality. So there is also no variadic function in Fortran, but you can rely on multiple binding, the scene binding to C-variadic functions, so functions such as printf, or when you want to interact with a database system, which have to be variadic to express long select or long query. So you have some way to get rid of the problem, but not in a very satisfying way. Okay, so not much to say about the structured programming Fortran. The interesting part of modern Fortran is its ability to harness the array and to get rid of loops and write refactored code, lean code. You will sum arrays, conformant arrays, arrays of the same size, of the same rank, can be added, multiplied in the Hadamard sense without expressing the loops. You can map functions on array with the elemental function. You can reduce your array with sum, product, and you can have dot products of vectors, matrix multiplication, reshape your structured data with reshape, and finally use do concurrent. So where is some expression that allows you to have some value for your collection, for your array, when some mask is on, and where it is off, you have a different value attributed. Okay, so if you want to get the most concise code, you will use array expression. It's nice in the sense that hopefully the compiler should see this array expression as explicit parallelism or implicit parallelism. You enhance your readability. Okay, so for loop, I just mentioned it, but don't use it, rely on do concurrent loop. It allows independent iteration, and as we will see mostly next week with GPU and Fortran on GPU, this do concurrent loop can be optimized by compiler for multi-threading or GPU execution. Okay, so what does it look like? So you will define your arrays. Here there are vectors of size 10 on rank 1. And with this vector, you can multiply two vectors and add some constant value that will be promoted to the corresponding vector. Then assign it to a conformant array, which is C. You can take the square root of this, which will apply automatically to all the elements. And in the case of a square matrix, you can transpose it and add it to its transpose to symmetrize it. Okay, and then you divide by 2, but you see the pattern. So as I told you, the for loop was limited to array assignment. So when you wanted to set diagonal element to 0, you could rely on this explicit index A of I is 0. What you can also do in for all is have some mask, some Boolean condition on top of the list of index that you want to take into account. So for all the indices from 1 to 100, apply this formula only when the initial value is positive. So it's kind of a conditional decrement. So this first do concurrent loop would not be possible because of the if inside. Would not be possible with a for all, I guess. You can also have reduction in your do concurrent list, do concurrent loops. And you can have some pretty elaborate aspect. Plus, when you have a nest of loops, you can express these in only one statement. And with Fortran 2018, you can express which variables are local to the loop, which also helps the compiler to go further. So some aspects that we'll not play with today are co-arrays. This has been designed as the follow-up of MPI, so for distributed computing. So it's on the same page as the Annex E for the Ada language. For distributed computing, you will compile one copy of your code and you can execute this copy on multiple machines, and they share a view across the network. So some compiler will let you play with your co-array Fortran on the same machine with each processor being played by a separate thread. But in principle, when it works, you can go across the network. So I have not found the dining philosopher problem dealt with co-array, as this is a classical one. This example here is another classical one, the Santa Claus problem, which was first tried in Java in '95 and then in Ada. We can play with it in Fortran. Here I just display some comments to share the fact that this is really painful to have co-arrays. You will depend on some MPI environment. You will have to run it with very specific version of your compiler on your libraries. So HPC is very reliant on given hardware, and you pay the price at the software level. So sorry for exemplifying once more with the same old project of electron capture on supernova. So colleagues of the theory group in IPNO came to me because they wanted to improve to speed their code, and we have all been exposed to the classical story of the supernova. Pressure gets so high that electrons go into the proton and turn into a neutron plus a neutrino. Yet, in the core of some massive star at the end of its life, you don't find a lot of lone protons. They are always in nuclei. So to take into account these nuclei effects, they had written a program to compute a cross-section for all possible nuclei type in the Valley of Stability and beyond. And it was painfully slow. It would have taken roughly one CPU year per nucleotide. So after some improvement, starting with profiling, so perf that Adrien has described us yesterday was not yet of use, but we did it with gprof at the time. We audited the various libraries, we changed the memory management, and we started to put the data structure in some order where the compiler could see some possible vectorization. And we started with the first 55 speedup, which is nice, so only 20 years of CPU. And once written, the program structure displayed a lot of concurrency. It was a big nest of loops. So in fact, the three last layers of the loops were written in C, while the two top layers were written in old Fortran. So this was not as nice as what you can see on the slide, but all the conditions were here to be in the paradise for a parallelist because a lot of independent loops were at play. Between 100 million and 10 billions of iteration only for the 4 inner loops. So you can express a lot of concurrency. The first attempt after this initial 55 speed up, factor 55 speed up, was to really start parallelization. And it looked easy. So the usual answer for parallelizing your code in old Fortran was using OpenMP. In modern Fortran as well, but we will see even better ways. So you have to tell the compiler using these special commands, which we call directive, that the following loops will be a parallel region where you have these two private variables and all the other variables should be shared between threads. Starting getting their initial value from the following commands. So yes, commands of the old Fortran world. And then it led to a seg fault at the entrance of the loops. So the usual reaction would be to use Valgrind in this case, but everything was relying on static arrays, big static arrays. And so Valgrind would simply drop out and say, too big for me. The code had to be compiled with the memory size equal medium. So when you have this compiling option, memory size is low means less than 2 gigabytes of data on code. Big is more than 2 gigabytes of data on more than 2 gigabytes of code. And medium is when you have only more than 2 gigabytes of data. So it had to be rewritten. And the colleagues in Idris told me, oh, you have 8,000 lines of C, you have 6,000 lines of Fortran, write everything in a single language. Of course, the language of choice was Fortran 90. And adding OpenMP on top of this. And when converting to Fortran 90, we now had 3 compilers, the Intel compiler, the J-Fortran compiler, and the PGI Fortran, the ancestor of NVIDIA Fortran. But this also led to 3 segmentation faults, and still no Valgrind because it was not so easy to transform all these static arrays. Okay, so faced with these problems, Playing with the program, it turned out that the code was in fact a fast spherical Bessel transform. So in principle, it can be expressed as a fast Fourier transform plus some work. So it could be rewritten in a lot of ways. Okay, so don't speak about vectorization. So we chose to move to GPUification of this code and use OpenACC that we'll use next week, which was very similar to OpenMP in the sense that we have directive with this command $ACC. We describe which data are present at the start of the parallel region or should be created on the device. We also express the parallel loops, and in this case, we say that we'll collapse the following 3 loops. Then inside the external loop, we will also collapse the 2 inner loops, possibly using vectors, SM elements of the GPU. And here, we have a sum of products of matrices, and the idea would be, why not write it as a matrix product? So a lot of things in this example have a spider sense tingle because we see that these loops are not do concurrent. Why? I said that the iterations were concurrent. And here we don't express all this set of loops as a single matrix multiplication. A complicated one, but why is it so? So when you use OpenACC, you have to use these usual do and do loops. So it's counterintuitive, but it's some already old technology, OpenACC, and we'll see next week how we can compare the two ways of using the GPU. Another aspect was that even if the QBLAS library would do an excellent work of computing the matrix product of these two arrays, the NVIDIA compiler did not automatically translate the matmul to the QBLAS. And it depended on the version of the compiler, the version of your GPU, the compute capability of the GPU. So even if we are not speaking of GPU today, the idea is when you push your compiler to the limit, you will meet problems that are not really a language issue, or for what it's worth, it's not a problem of syntax. It's the compiler are not yet ready. Okay, so this should be left to the next week GPU aspect. But you can use so-called CUDA Fortran, where you will have extra attribute in your, like here, you have the device attribute to tell the compiler that your real arrays xd of n and yd of n are in fact declared on the device. So this can save you a lot of memory transfer on the corresponding speed problem. On top of which, you have the CUDA style of kernel expression using this bracket. So this is only for NVIDIA environment, and it cannot be ported elsewhere. Okay, so now we'll discuss the problem at play today, computing a Gray-Scott reaction with Fortran. And you can find on the GitLab here or with the images on Must and Kubernetes, the starting point as well as the solution to the problem. So as I said, the first step is to get some makefile. So here this is a bit convoluted as I made sure that the makefile would adapt to various compilers, including IFX, Intel compiler, NVIDIA with NV-Fortran, and J-Fortran by default. And they all have various options to compile. Okay, so you can also define pre-processing strings so that you can stamp your binary and know which version is running. My makefile have usually a lot of targets because not only I want to compile my code, as is the first target, build the main executable, but also we want to execute it with perf on top of it, execute Macao on the resulting compilation to get depressed. Then mem check the usage either with Valgrind here. You can also produce the documentation with Doxygen and use the various linter I told you of. Check if we had 77, Camfort, Lizard, Simian, Fortitude. And also, from time to time, counting the number of statement line of code to see if we can reduce the mass from one commit to the other. And also produce a word cloud in order to see if the variables are really badly named or simply non-expressive. So here we have a lot of PR, which is the extension for the precision of the literal values in the code. So this is the generic precision that I can decide at the start to be float or double or extended or quadruple, and maybe sometime half precision with NVIDIA. We have the two U and V main arrays for the Gray-Scott reaction. And some of the names that appear less often are a bit better chosen and more meaningful, such as diffusion rate, stencil, feed rate. This tells a story. So I find workloads a way to get some view of our code. Okay, so these are the targets you will find in the... Oui, yes?
On your GitLab, when I use Docker with it, I don't have permission to nothing.
So from Docker, you don't find the .git because the image was...
No, when I try to build...
This is...
The sources directory you...
Yes.
Make the show.
I should get it on some other account than root. Is it? Okay, so sorry, I'm a beginner at Docker, and I will learn with you. Okay, so for today, you should not be too dependent. You should not depend too much on the Docker because Fortran is quite easy to get, but yes, better. You will find in the /home/examples the version that was in use at the time, even if it's not with version control. Okay, so as we should do, I put all the settings in a module, Grace Code settings, that rely on some use precision. So use precision in turns rely on the ISO Fortran and the intrinsic module to define the precision as real 32, and then later all the floating point value I use are _PR, which can be changed from real 32 to real 64 by changing only this line. Okay, so you see the classical commenting with Unicode at the end of lines. We have dynamical variable UV and UNUV for the dimension. So maybe in the version in the image you have U0, V0, U1, V1, and of course the corresponding Laplacian, as well as the stencil coefficient that are defined with multiple stencil, and then we choose one. The initializing subroutine will use a so-called name list here. Name list is a bit like a common. It's a set of variables that we have. Okay, so it's not here. Okay, we have a list of variables that we can read as in one go. It is defined in the code in this way, a list of variables with a name. And in the file, you have the name of the name list and the values of the constants with their name. So this is a very convenient way to avoid parsing by yourself your configuration file. So I run the Alpine Canna image on the LSKCD server that was used this morning. So on the slide, I have shown you a makefile that was made by hand, but the modern way is to go through CMake. So we have the definition of project Grace Code in Fortran. We declare the Fortran compiler as Fortran. We set the source as the main program Grace Code that I've shortly shown you. And we will use a module that I designed to interact with the HDF5 library in order to initialize the HDF5 file, define the slice in the slab, save them, and close the resulting file. For a start, we will only add this HDF5 component to the package. Then we defined a release on the debug options. For the various compiler. What goes afterward is not of interest for the start. In order to benefit from colorization, I move to Codium. Okay. So the version on the screen is a bit more recent than the one on the slides. We find the settings module. So we have the new naming scheme of U0 on the U1, V0 and V1 because we'll move between two memory locations for the two arrays. For a start, we'll consider that we do not write the result. We want to see the speed of the computation before checking how bad it is. All the variables declared here being initialized are static. They are saved, but they are not constant as they will be modified when we read the name list that I told you of. So we have been discussing between the naive stencil for the Laplacian, the ISO stencil, which has more aesthetic results. And if you are really a purist of partial differential equation, you should use either of these two last ones that have better numerical properties. Okay, so compared to the slides, you see that the name list, the two name lists have been fused together. We don't separate between physical parameters and computing parameters in this case. Here we we have the file name that will have the HDF5 data, as well as the name of the dataset into this HDF5. This subroutine in turn check that the configuration file exists, and if it's the case, it is read with the name list format discussed before. We have some check because we can also write the values of the variable according to the namelist format on the standard output. Standard output, which is only some redefinition of the intrinsic output unit. And then some setup of the file, which, as you can see, setup file is defined as coming from the HDF5 utils module. So this is a good practice to limit with this only statement what you take from one given module. So if you want to go beyond the old habit of using commands with all the data they could bring, you can specify to the compiler that only this partial data is known from this given module. Some of the linters I told you about, such as Fortitude on Camfort, will send you a lengthy warning about this rule not being respected. Okay, so this version that I provide you with is a very naive implementation. I let you practice with it to get it compiled, and then we'll see how we can improve it. So the first improvement should be immediate. And then here, this write-out solution routine is a very naive one. We should not use this as we will be writing to HDF5, but you can use it if you want to see the data. Well, you will not really see much as this is an unformatted write statement, so it will be written as binary data, the most concise way. And you will see in turn that this write way of getting your data out is in fact rather slow compared to HDF5. And then the main program is quite short, okay, less than 40 lines, 30 lines. So I already put the OMP statement on each side of the main loop, but it's not so easy, and it will not work like this. Okay, so at start, the output was, this open statement was here to help using the write we have seen before, but we'll have to look at the solution for the HDF5 use. Okay. So it compiles. Okay, this version is complaining about H5 version, but this is a warning only. And so you can see the initial check of the value we'll play with. So besides some rounding error in the display, we find the diffusivity of U and V, the feed rate and the kill rate. The size of the image is right, but we'll take only 320 steps to keep it within a reasonable duration. Okay, so here it took 1 minute. So we certainly have some problem. I give you some time to play with the CMake and try to improve the speed. So we take some break. So we'll see after the break.